Hey everyone, welcome back to the Newton's Law video. And so in the previous lesson or video, we had looked at example number 6, and we unfortunately ran out of time, so we weren't able to finish that up. But so what we did is that we did have time to find the acceleration, and we needed our acceleration in order to find to calculate the force, which is essentially what the question was asking for. So now that we've actually calculated the acceleration, we can now go ahead and find our force. So you know that our force is equal to your mass times your acceleration. So the mass we know was 55 kilograms times your acceleration, which we had calculated, was this very big number of 197,633.33, with our 9 being that significant digit. If you plug that into your calculator, you're going to get a ginormous number, which is 10,869,833.33 continuing. With our sig figs here, we have two significant digits. So when we're going to round here, our answer here rounds to 11 million. Which that one there is a very large number. So if you guys remember back to our Physical Science 20 class, and we talked a little bit about it in our first unit, but when we have giant numbers, we should express this as our scientific notation. So our answer here for force should be 1.1 times 10 to the power of, we have 1, 2, 3, 4, 5, 6, 7. So we're moving the decimal point 7 times, so our exponent there is 7. And here we're talking about force, so our units are newtons. So then just to finish off this question here, we can write a sentence. I'm just going to be awkward and write it at the top of my next page here. So here we could say that the force on the shell is 1.1 times 10 to the 7 newtons. Now you guys could include I guess a direction here if we want to make it velocity. I would be fine without a direction. So if you want to include a direction, you just could state forward. But in this case, since our velocity wasn't given a direction, we don't have to state a direction in this as our final answer as well. Okay, so let's move on to example number 7. So this one here is going to have similar concepts as to what we did in example number 5, where we're going to be working with an angular type of force. So two people are dragging a canoe out of a lake onto a beach using light ropes. Each person pulls the canoe at an angle of 20 degrees, and each exert a force of 60 newtons forward. The frictional force exerted by the beach on the canoe is 85.0 newtons back. Calculate the net force on the canoe. So what we're looking for here is we're looking at the net force of the canoe. So that's the overall forward or motion to the right of this picture. But we do know that there is some resistance because the canoe is going to be dragging on the sand. So that's what this frictional force is. So just to draw our object here, I know that a canoe definitely looks like a square, but just for simplicity's sake. So we have this force that's pushing back 85.0 newtons. And we know that each person is overall exerting, so here it says 60 newtons forward each. So we're going to have one person pulling at a 20-degree angle like this, and the other person is going to be pulling at a 20-degree angle like that. And here it's, just according to our diagram here, it is at a 20-degree angle for each person. So in order to find our overall net forward or motion, or that force to the right, we need to calculate what total forward force is being applied by both people pulling on the canoe, and then find that difference between the two forces. So we're going to find the forward force, the force that's going forward. So that's looking at this horizontal component. So just like what we were kind of seeing with the last example in example number 5, if we were to connect these to create right triangles, we can use our trig ratios to solve and find this horizontal component or that forward pulling motion. So here we have an angle. We're going to be looking for the adjacent. And we have the hypotenuse. And that tells us that we're going to use the cosine ratio to solve this. So we have our cosine of 20 degrees is equal to your adjacent, which is what we're going to look for, so we can let that be x, over your hypotenuse, which is the 60.0 newtons. We can write our cosine over once, so we can cross multiply to solve. So we have cosine of 20 degrees times 60 should give us 56.38, and that's a rounded value for our horizontal or that x component there. And before I move on, I'm just going to keep track of sig figs here. Here we had 3 sig figs because of the 60.0. So here our 3 will be underlined just to keep track of sig figs. So now that we have this that horizontal component from each person, remember this is from each person, we can find that overall net force. So step number 2 here is the net force. So that's equal to this 56.38 newtons going forward from each person, so we have to write that twice. And then we need to subtract this frictional force that's acting as resistance. So we're going to subtract the 85.0. So if you guys either can do that in your head, or if you guys want to slap that into your calculator, we should get 27.76 as our answer. And then just to keep track of sig figs there, here we're doing the adding subtracting rule, so we have to work with our least precise measurement. So here we have 1 value to the right of the decimal, 1 value to the right of the decimal, and once again 1 value to the right of the decimal, meaning that we have to go to 1 value to the right of the decimal for your answer. So our answer for this actually is 27.8, and we're doing newtons, and this case here we're working with our forward direction. And so in this type of example, we are given direction within the question itself, so you should include a direction in your answer as well. And then we're just going to finish this off with a sentence. So the net force on the canoe is 27.8 newtons forward. Okay, moving on to example number 8. So a store sign that experiences a downward gravitational force of 245 newtons is suspended as shown in the diagram below. Here we're going to calculate the forces of Ft1 and Ft2 exerted at the point at which the sign is suspended. So this question here is going to be split up into 2 parts. We first need to find our Ft1, which is this portion right here, and Ft2, which is this portion right here. So what I'm going to do first is, since we have this nice diagram here, I'm just going to add on to this rather than drawing my spectacularly awesome boxes for our force. I'm just going to include in here what we know here about this gravitational force. So on this sign right over here, there's going to be a downward force of 245 newtons. That's going to be really important in order to solve for Ft1 and Ft2. Okay, so our first step here is we're going to find that first force, which is Ft1. So in order to solve for our force, our first force that we're going to be looking at is this one right here. We can once again make a right triangle. So we have this angle here that states that it is 55.0. And that's all the information that we're given right now. But one thing that I am going to say here is that we actually do know another piece of information. We can use this gravitational pull. We know that this sign isn't moving up or down, which means that that force pulling down is also equal to that force pulling up. We know that there has to be a balance if that sign isn't moving. So that means that there must be an equal force of 245 newtons up if this sign is not moving, okay? So here we actually do have a second component to this triangle. So here we're given an angle, we have the opposite side, and we're looking for this part right here, which is your hypotenuse, which I'm going to label x. So you have your opposite and hypotenuse, which tells us that we're using the sine ratio to solve for this. So I'm just going to fill in my values here. So I have sine is equal to 55 degrees. That's equal to your opposite, which we know is 245. And our hypotenuse, which we don't know, which we can let be x. I'm going to write sine of 55 over 1 so I can cross multiply to solve. So we have sine of 55 times x, or x times sine of 55, is equal to 1 times 245, which is 245. I want to get x by itself, so I'm going to get rid of this sine of 55. So I'm going to divide it. Plugging that into your calculator, you should find that you get 299.09 as your answer. And then we have to make sure we count for sig figs here. So here we have 3 sig figs for this 245, and we're not going to worry about our angles here. So our overall answer should have 3 as well. So that means that our answer here is just 299 newtons for FT1.